like to welcome everybody to the very first brown bag webinar we're having for 2018, and we're very proud to have Dr. Anthony Vasily here with us. You can see him there, and he will be pulling up his PowerPoint soon. And he is the manager of the Offshore Model Testing and Structural Design at the University of Maine Advanced Structures and Composites Center. And we are very fortunate to have him here with us today. And without further ado, I'd like to welcome you, Dr. Viselli, and take it away.
Thank you, Holly. Real pleasure to be here for this webinar. Again, my name is Anthony Vasily. I work at the Advanced Structures and Composites Center. I've been here at the center for over 16 years. First starting as a student here in the engineering program and gradually taking on more leadership roles here, specifically in offshore structures design. In addition to this project, I work on several other projects as well as manage our new offshore model testing basin here in the center. The goal today is to tell you about a new technology we've developed, we've been working on very hard for over a decade. It's a new floating foundation made of concrete that supports a wind turbine and allows the U.S. to access high-speed winds off its coast. There's currently enough energy within about 50 miles of the U.S. coast to power the whole country over. And the goal here with this technology is to reduce that cost to be on parity with conventional forms of electricity. So today we'll be sharing a little bit about our story with this technology, how we got there, why we chose to go in this direction, and how it can benefit the state as well as the whole country. And at the end, we'll have some time for questions. I'd like to also acknowledge my colleague, Dr. Habib Dagger, is the director of our lab and has been really the driving force behind this project, who I work very closely with. I'll start first just a little bit and mention a little bit about who we are. We're the Advanced Structures and Composites Center. We're part of the University of Maine. We're essentially an R&D facility that is almost completely funded through competitive grants as well as working with industrial companies. So it's an R&D lab founded about just over 20 years ago. There's 180 faculty, staff, and students that work here in the center. It's a 100,000 square foot laboratory. Over our duration, we've educated about 2,000 students who get paid to work in this lab on real projects. So there's a large educational component in how we train a future workforce. The center is really focused on bringing advanced materials into construction, so taking new material systems, new structures, and bringing them into the real world. And as a result, we've actually spun off a number of companies that are using these technologies today. This map shows our partners and clients. We're a global institution working not only in the U.S., but all around the world on a variety of different projects. In terms of in the United States, we've brought over $110 million worth of R&D funding from outside Maine to Maine, and working with most of the major funding agencies in the U.S. federal government, including NASA, NSF, the U.S. Army, Department of Energy, and Department of Defense. Received a number of awards and honors because of the work we've done, over 40 national and international excellence awards for our research. Some of the top ones are here, including some from the top engineering associations in the country, including the American Society of Civil Engineers and the American Council of Engineering Companies. I'll talk now about some of the other technologies we've been working on, just to give you a sense of the breadth of our center. This is a composite arch bridge system that we've developed that was recently recognized by the White House a few years ago as a major instrument of change. It's really the Innovation Award. And this technology is now being used by the Advanced Infrastructure Technologies. It's a new company. It's been spun off and has licensed the technology. And they've built over 24 bridges using this concept. We've also worked on another bridge technology. It's a composite concrete hybrid bridge. It's actually the longest composite bridge in the world. We were involved in that project. It's over 540 feet long and 32 feet wide. It was opened in 2011. We also worked on managing and designing the first all-composite hull for the U.S. Navy with another spin-off company called Hush and Defense Composites. This is called the Mako. The boat itself was intended to replace an aluminum version of the hull that, because of the aluminum structure, actually vibrated and caused injuries to the occupants of the vessel, which was the Navy SEALs, the Navy SEALs vessel. And this boat goes extremely fast, and the wave slamming forces was causing injuries such as dental fractures and spinal injuries to the Navy SEALs. So the idea was to use a composite hull, which is a shock absorbing, made of shock absorbing materials. So this is that hull. So it was built and during its maiden voyage down in Booth Bay area here in Maine. This is during some of the initial sea trials of the vessel. And doing some of the extreme maneuvers. This is a top 180-degree turn at full speed. That's one of the maneuvers that was required to demonstrate. In the area of wind, we are one of 3 facilities in the United States that does wind blade research and structural testing. This is an aerial shot of our laboratory. You can see here. This is a 56 meter long, so about 160 foot long blade that was brought into our lab and was tested for commercial entity. So this blade is brought right in here and mounted onto a wall, and we simulate the equivalent of 20 years of wind loading to ensure that the structure meets all the appropriate requirements and standards, engineering standards. So this lab has been open now since 2009, and this is a video of our blade testing. This is the fatigue type loading. To give you a sense, this tip of the blade is moving, plus or minus by 15 feet. So it's a very dramatic loading that we do, very large structural scale testing going on in our laboratory. In terms of offshore wind, this is a video of our floating technology, which was deployed back in 2013. We deployed the first floating offshore wind turbine in the U.S. It was the first grid-connected unit. The goal of that project was to study how these units survive extreme waves and winds. So this unit was deployed offshore, Castine, Maine, and in a site that produced scale wind and waves. The unit is 1/8 scale itself, and that was the whole purpose of the experiment, was to show how it would survive these types of environments. Floating wind is a newer concept that's being researched by a number of countries around the world. There's already offshore wind turbines in Europe, but they're all fixed bottom. And only recently, in the last, say, 10 years or so, has floating wind been looked at. Why floating wind? Floating wind is, the reason why you go in that direction is because the water depths drop off in a lot of regions of the world, including the US and Japan and other parts of the world. The fixed bottom technologies just really don't make sense at those depths economically. So these floating technologies, the idea is that you can capture more of the wind resource. You also can build the hulls completely on land and minimize offshore construction. So that's what we're demonstrating here in this video. This unit was tugged out from a port. It's constructed on land and then towed out and hooked up to some moorings. So we'll talk more about this technology here today. This is the hull that was launched in 2013. You can see the unit. It was built at Chimbro's facility here in Brewer, and then picked up and launched into the water and then towed down the river with the tugboat that you saw earlier. This is during a launching ceremony we had with our congressional delegation with over 1,800 folks who came to see this event. I'm going to show you now a little bit of footage of the unit when it was installed at the site. This is what we call a once every 50-year type storm event. So we deployed this unit in a region where we thought we'd see these types of conditions. So you can see the unit, it's floating and it's moored with 3 anchor chains and the turbine's running. And this is going through a very nasty winter storm called Winter Storm Electra that occurred. And the wave heights relative to the size of the unit were the equivalent of a 50-year storm that would occur out far offshore in the Gulf of Maine. So the purpose of the experiment, again, was to subject this unit to scale equivalent events so we could learn how these structures behave, how they endure these types of environments, and then ultimately compare them to our engineering predictions that we've done. There's a number of sophisticated computer tools that predict these motions and ensure the safety of these and reliability of these structures. So a little bit about why we're doing this, giving you a little bit more of the background. Really all this this idea was conceived back in around 2007-8 when the price of heating fuel and gasoline went up to about $4 a gallon. For the average Maine family, that's about $10,000 a year in costs just to go to fuel homes and heating and so forth, which, looking at the average income in Maine, is a very significant percentage of people's income. So the question was, if this now comes down to $2 a gallon, well, right now the gas at the pump's probably $2.60 or so, at least it was yesterday when I filled up. That comes down, it's still a significant chunk, and by all accounts, people expect those to rise again. So the idea was, what other options do we have in Maine as one of the most heavily reliant states on fossil fuels? What other things can we look at? What other resources can we find? And if you sum up all that money in the state due to gasoline and heating, that equates to around $6 billion a year in petroleum natural gas. And that's data from the U.S. Energy Administration. So this is really the impetus for why we were looking in this area, looking at how can we harness different things. The state of Maine uses about 2.4 gigawatts of of energy each year. And offshore the state of Maine, we have about 156 gigawatts of wind. So even if we only harnessed a little over 1%, we could essentially have enough energy here just within 50 miles of the coast to power the whole state. This is a map of the United States, showing you how much offshore wind capacity the whole country has. These colors represent different wind speeds. Essentially anything with a red or to brown color, you have a very good wind resource for a wind turbine to be deployed. So if you look here around the country, you see red here off the West Coast, you see red here starting Massachusetts up. And off the coast of Maine, you notice we have a very, very big area of red and orange that's attractive. And that's where that 156 gigawatts of wind. These are numbers generated by the U.S. Department of Energy. They have a research lab called the National Renewable Energy Lab. So these are independent numbers provided by them. Right now, Europe leads in offshore wind. They have over 12,000 megawatts or 12 gigawatts installed. And this is what these foundations look like. They're typically jacket steel structures that are in water depths typically of less than 120 feet or so. The challenge we have off the coast of Maine is our waters drop off to 200 to 300 feet pretty quick. And so that's really the challenge for us in the U.S. is the depths of the waters, and how do we harness these high winds to going forward. So what we did before we went into the water in the 1/8 scale, we did a lot of engineering homework looking at different ways to capture this resource efficiently using floating technologies. We did this research in a basin, a wind wave basin, which you see here. This is at the University of Maine. It's a wave tank with a wind tunnel on top of it. And the objective of this facility is to conduct very controlled experiments at a reduced scale, typically 1/50 scale, and assess different designs, performance, assess how well they endure, how much power they can produce, and essentially build up the justification to move forward with larger prototypes and eventually commercial scale projects. So this facility here is the only one in the country that can test floating wind type structures and produce data that can allow you to progress technologies to the next level. This facility is what we're showing here in this video is the Wavemaker in action. The waves are generated by 16 roughly 2-foot wide panels going across. and they can all act together as they are and throw waves to the other side of the basin where they crash on a beach and get dissipated. This is looking down the length of the tank. We have the waves running towards the wind in this case. So that was our wind tunnel there. And here's the wave paddles pushing the waves down the tank. And those can be adjusted, and both height and period, to simulate different conditions that you'd find at full scale. So this is very much like the movie Honey, I Shrunk the Kids, except for it's Honey, I Shrunk the Ocean and Honey, I Shrunk the floating wind turbine. So this piece of equipment, this large wave tank and wind machine and wave paddles, is really a test bed for us to try out new concepts. What you see here in this video are the waves breaking on the beach. We have a wave dissipation beach on one side, and that prevents the waves from reflecting back and disrupting the quality of the system. So this is the wind machine. You can see the fan spinning here. This facility can simulate the equivalent of over 100-foot waves and wind speeds over 200 miles per hour, which is bigger than anything you might see in the U.S. So this thing can basically simulate the worst conditions on Earth. This gives you a sense of what the scale looks like. So 150 scale, this is, over 100-foot wave. So how do we know our wind turbine will work? We did one of these sophisticated experiments. We built a fully scale model. All the mass and the behavior of this unit, both the naval architectural properties as well as the mass of the unit, are scaled following a technique called fruit scaling. It's a well-known science, been used in the shipbuilding and offshore oil and gas industry for many years. And we measured rotor torque, accelerations, loads at the nacelle level, as well as global motions of the hull. And all this data is feeding back to a computer. In real time, our engineers can study that information. This hull was built here in our laboratory. We have sophisticated manufacturing equipment, large 3D printers, as well as welding, CNCing. You can see here's the hull at different stages of construction, as well as the blade being constructed here. So it's a very careful science. The model building is very exact and in particular. This shows you here some of that testing that happened. So this is underwater. You can see what the hull looks like. You can see the mooring chains running from the side. And this is expected behavior at once every 50 years. And another thing to keep in mind in these tests is that because the scale experiment, this is a scaled experiment, all time has been accelerated by roughly a factor of 7. That's part of the science behind this. So these motions, if you're looking at them full scale, would be about 1/7 the speed. On the video to the right, what you see is this is above the water. And you can see the turbine is operating. And then you can see, just for reference, a small boat, just to give a sense of for scale here. So that was the type of homework, if you will, that went into this project prior to building the 1/8 scale unit, which was launched that we started off the presentation with. So I'll spend a little bit more time on this unit, and we'll talk about some of the lessons we learned, and then we'll talk about what we're working on next, which is full-scale demonstrator, 2 6-megawatt units offshore Maine. So the 1/8 scale project, the overall goal was to validate the design behavior. And when we say design behavior, really the loads, the motions, the survivability of this unit in any condition it might see in the Gulf of Maine, any wave or wind condition. So it's a fruit scale test that, again, that well-known science. It's a 1/8 scale version of a 6-megawatt turbine. And it was deployed at a sheltered site where it saw 1/8 scale wind and waves. We needed a 1/8 scale site for a 1/8 scale prototype. And then we also built this unit out of the same materials that we would construct the full-scale unit. So the hull is made of concrete. It's made out of concrete because there's a large concrete industry in the U.S. that can be mobilized cost effectively at the prices that are needed to keep cost of offshore wind low. Steel hulls can be done, but in this part of the world, it's very difficult to produce them at the prices that are needed for offshore wind. You might be able to produce them in Asia, but that's not really our goal here. Our goal here is to use a hull that can be built cost effectively in the US and ultimately create jobs through that construction effort. The third and fourth goals of our project was to validate engineering tools. We call them coupled aeroelastic hydrodynamic numerical tools. These basically combine all the wind turbine models with the naval architectural models and structural models, and making sure that those predict the behavior of this unit accurately, so we don't put units out there that might not survive. That was a big deal. A lot of engineering work had to be accomplished to do that. And this test was essentially, it was a real offshore test to validate that those tools work. Here we are constructing the unit. So this unit was built in our laboratory working with Chimbro, a large civil construction company here in the state. So here we are, we're actually casting the floating unit so that you can see parts of it are cast, and then you can see the formwork, the concrete formwork being erected here. And these are some of the construction workers. So they're actually pouring the concrete from the top and surveying that as they bring that together. Here's the completed unit. And a comparison between the 1/8 scale and the 6 megawatt. All right, let's go ahead. This is some testing we did here at the dockside. We're essentially pulling on the unit with the crane and looking at some decay tests, looking how it behaves as we perturb it, and measuring the period of that unit. So it's a key test. We're also doing some incline tests to ensure that it's been built properly and has the right static stability. Following that, we towed this from Brewer down the Penobscot River out to Castine. So it was about a 40-mile tow. Here we are going through the Penobscot Narrows Observatory area in Maine. So it gives you a sense of the route that we came down here. And what you see here in this graph in the top is a measurement of the force predicted in the tow line, and then what we measured. And this was showing a very good agreement, essentially validating the towing methods. We also have on November 27, 2013, we received one of the largest wave events. You can see the wave well, relative to the unit height. It's about a 70-foot wave at full scale. And what we're going to show you here is some of the model validation we've done. And I apologize here, there's a format issue. I'll just fix this. Bear with me here. So this is some of the real-time data we got in blue versus our numerical tools called FAST in red. And what we're showing is the acceleration of the unit at the tower base. And you can see how well we're able to predict over a period of about 100 seconds the motions of the unit. And then here you have your tower base heave acceleration. So heave is vertical, sway is side to side, and what we're looking at is essentially the comparison of those two signals, and you can notice they overlap quite well. So these are the types of studies we've done and wrote a number of reports that were submitted and reviewed by the U.S. Department of Energy, essentially validating not only the technology behaves the way we expect it to, but that our engineering tools work and have been checked against real data, which was a major accomplishment in this field. And we've presented that at a number of conferences and helped further that state of the art. Ultimately, this has all helped to de-risk essentially a full-scale deployment, which we're working on now. This is an aerial shot of the project off Castine. If you're familiar with Castine, this is the Dice Head Lighthouse. And we're about 1,000 feet offshore. This, again, this is moored on with 3 mooring lines coming out radially here. And then we also had a mid-ocean buoy measuring wind speed heights through the air up to 600 feet and waves at the same time. So that's really the data buoy and then the prototype. So this, and just to summarize that effort, we in June 13th, that's when we officially connected this unit to the grid. It was actually the first offshore wind electrons to start to flow to the U.S. electricity grid. So this was the first offshore wind turbine. You can notice this is a plot here from the Global Wind Energy Council report in 2014. This is essentially a plot of all the installed capacity in the world, and this put the U.S. on the map at 20. It's a 20 kilowatt machine, so it put us on the map there in terms of essentially placing the flag. Since this time, there's been 30 megawatts now installed off Block Island, which we'll talk a little bit more. So I'll talk now about where we're heading next. So because of the success of the 1/8 scale, because we were able to prove our engineering tools work, we were able to tow it, prove the towing methods worked, we demonstrated the technology. Essentially, we had de-risked it to the point that the U.S. Department of Energy decided to invest in a much larger project. So this is a program called the Advanced Technology Demonstration Project. That's the U.S. DOE program. And so we competed for this work against roughly about 70 other groups submitted proposals. We submitted our proposal with Chimbro, and it was called the New England Aqua Venice Project. It's a 6 megawatt floating system, the same technology we've been discussing, off Monhegan Island. And since that initial proposal, the DOE's down selected from 70 to 7, and then now down to 2. And we're the one of the 2 projects still left in this whole very competitive process. The other project is in the Great Lakes region. So this project is now moving forward. The goal is to demonstrate 2 6 megawatt floating concrete turbines by 2020 in the Northeast U.S. The floating concrete technology that we developed at Maine can capture about 60% of the U.S. offshore wind resource. That's where they have water depths over roughly that 150 foot depth. That's where this technology becomes viable. It's less sensitive to site specifics. You can essentially, when it's floating, it's decoupled from the seabed. So you essentially can build these hulls, almost repeat the process for different sites around the country. It's easier to mass produce because we're using concrete bridge technology. And the levelized cost of energy, LCOE, for utility scale has been estimated by an independent by the U.S. government to be less than 10 cents a kilowatt hour for utility scale projects. So this is where we're heading. So our whole team here at UMaine have been marching towards this goal, and we'll give you an update on that here for the rest of this webinar. So here's right here. It's a $40 million US DOE grant. The units will be deployed just south 2.5 miles of Monhegan Island, and there'll be a cable run back to the mainland to connect to the grid. This is the project site. There's a test site called the University of Maine Deepwater Offshore Wind Test Site, which was established by the Maine Department of Conservation in 2009. This was a push back in 2009 to establish these test sites around the state for looking at offshore renewable energy technologies, including wind, tidal, and wave. And the University of Maine was awarded this test site after quite an extensive process, environmental process, outreach process. And this is what the site looked like. It's 2 miles, 1 mile, and it has a buoy also has been deployed there measuring wind and wave for about 18 years now. So this site will be the location for these 2 projects, two turbines, I should say. This is the buoy that's located at site, the types of data we've collected. So you can see the test site here. The buoy is deployed just about 1/2 mile west. measuring waves, wind speeds, current, temperature. All this data has been used, is being used to design the units and make sure they can survive these conditions. Very similar to say, an offshore oil and gas structure. They have similar data sets. They'll design these units to survive these types of conditions. So it's quite a well-known practice in terms of how to interpret this data and develop safe designs. There's been a number of pre-deployment environmental studies. There's a very large environmental and permitting team that will be learning on this effort. These will be the first 2 floating wind turbines in the United States at commercial scale, and there's a lot to learn here in terms of the ecological, geotechnical, and effects of these units. So that's one major goal of this effort. But before these can even be installed, there's been a number of studies. You can see these are essentially all the different types of studies, different types of environmental scientists who have been engaged, and the years when they've conducted studies. So you'll notice, for example, fish. We've been monitoring fish in 2010 through 2015, marine mammals, same duration, birds, essentially to look at a baseline at this site, look at how these different species are behaving, and assess whether there'll be a major impact, and also once the turbines are deployed, whether what kind of impact, if any, there is. So that's really the goal here. Essentially, these are all baseline studies, and have been required as part of our permitting process. So a very major, very rigorous permitting and environmental monitoring program that's been going on now since 2010. The project really has 4 main construction sites to make this happen. So if we look here, follow these yellow pins, you have the University of Maine here, located just in the center of Maine. Just south of that, we have the casting site will be done either in Hamden or Brewer. So right across the river, there's 2 sites there. Searsport assembly site will be where we'll assemble the hulls. And then New England Aqua Venice, 1 site. I apologize, this cable landing site is a little outdated. There's alternate routes being considered of where the cable comes on shore. So it's a little outdated, I apologize. In terms of next steps, in 2016, 2017, we're wrapping up the project design, and then be going through, starting the US DOE NEPA sessions, conducting additional ecological studies. These will be ongoing. In 2018, we start planning the hull construction. That will run though for quite a while, and in 2019 to 2020 will be in the installation phases of the project. In terms of the hull technology itself, what we see here is how we can build these units cost effectively. This slide is really goes to the title of this presentation in a very deep way. This is how we're going to get the costs down. Essentially, we make this hull in a very repeatable way, essentially a bunch of blocks, repeatable, identical shapes, and we can do that by using concrete. And this is a method that's being used to construct concrete bridges around the country today. So we're not inventing anything new, we're just applying it to a new industry, which is the floating offshore wind industry. So these sections are about the same size of large segmental concrete bridge structures that are being built. And the beauty of this technology, essentially, you buy a mold. So for example, for this column, you have a mold, and you can reuse that mold over and over again. And for these larger farms, you'd have a number of these turbines. And the turbines, essentially, you invest in the molds once, and then you start cranking these things out. And you can meet the production rates that are needed for a large project, which is roughly, for a large project, around 1 unit every week or so. And you can do the same thing with these lower structures as well. So this is really how the technology gets the cost down. And we've made our own estimates, but the U.S. Department of Energy wasn't going to invest its $40 million until we had independent numbers. So what was done was we had an independent third party called the National Renewable Energy Lab. It's a federal laboratory, And they did a levelized cost of energy analysis for this technology. So it's a LCOE, levelized cost of energy. And they found, this is a direct quote from that report, that for utility scale projects using the Maine concrete hull, they believe they could reduce down to 7.7 cents a kilowatt hour by 2030. So that's a huge finding that gets us into that parity with other forms of electricity today. The other major conclusion is the impact on U.S. manufacturing. Given the ability for the concrete hull to be built anywhere, it could be installed in both the Atlantic and the Pacific side economically, and could be an important step in increasing domestic content for offshore wind in the United States. So there's a very big conclusion for NREL to make that very big deal for NREL to make that conclusion, and that was really one of the main reasons we were selected to move forward. This shows all the area of the country that could be accessed using this technology in purple. The light blue is what could be accessed with existing technology from Europe. These are fixed bottom foundations. And then the purple is what you can get with floating. And this is why the Department of Energy is very interested in this technology. So you just look at how much more energy you could potentially capture with such a piece of hardware. Skip ahead here to this is the construction process. What we plan to do is construct these units. This is one of the methods we're looking at. This is essentially casting the base in a dry dock, looking at multiple options. But this is one option being considered, where we basically cast the unit. These are all concrete pours essentially. So we're basically forming up the whole hull, and then once you cap the top here, what we'll do is we'll essentially flood this area and then take it down the river. So this is one option that's been looked at. We have alternative means to do this here in Maine, but this is one such option that could work. We would then float the base down to Searsport, and then the erection of the remaining vertical concrete columns and the turbine would then be outfitted here as well. So you can see, get an idea here of the erection process, and then installing this unit. And this whole unit, again, is floating. So this unit can now be moved around and be positioned at its site. And that's a big advantage versus fixed bottom, which you have to do all this work. All this erection process would have to be done 10 miles offshore, which is a big cost and a lot of risk of weather conflicts. The waves are too big or the winds are too large to do any work. So this really minimizes a lot of the construction risk by doing this work inshore and then floating them out. So that really gives you an overview of what we're trying to do here in the near term. In terms of the long term, just a few statistics that have been estimated in terms of the economic impact an industry like this could take place. In the future, if we start developing this type of wind resource around the country, the UK estimates they'll have about 30 gigawatts by 2020. This is the current trajectory, which is equal to about $120 billion of investment, 60,000 jobs, and they're moving in that direction. In the US, the DOE has goals of 86 gigawatts by 2050. Again, a $350 billion industry, 175,000 jobs. In Maine, if we only developed 1 gigawatt of our 156 that we have, that could be a $4 billion project and 2,000 jobs. There are no plans right now to do such a project in the works, but just to put that in perspective for what could happen if we'd have to go through quite a process to take place. But this is just give you some statistics in different parts of the world. And as we add more energy to the mix, how does that start to change the way we use energy in this country? And if you just kind of start looking around at what's happening, for example, in the automobile industry, you'll notice that almost every major car manufacturer is moving towards all electric vehicles, and many have multiple designs across multiple different car types. Ford's recent announcement is a good example. Chevy, Nissan, Audi, and many, many others moving that way. And that demand for electricity could come from offshore wind. Similarly, how many heat pumps could be installed in the next 20 years and moving in that direction, start using the energy that way. To kind of wrap things up, I just want to give a perspective what's happening globally and how our project in Maine fits in. This isn't isolated just to the University of Maine. This isn't just something we're working on. This is really a race right now in the world to develop low-cost offshore wind technologies. And right now in Europe, the offshore wind costs are dropping very, very, very quickly. In 2016, so just a couple of years ago, 3 major European offshore wind projects priced at 5.6 to 7.2 euro cents a kilowatt hour, which is very, very low, very historic prices. In July 2016, a very similar number off Netherlands. Again, 2016, 6 cents. December, 5.5 cents. So Europe, they're already starting to hit those numbers with fixed bottom technologies. So the price of wind is starting to hit those targets of being on equal footing with others today. In terms of floating wind, the United States is not the only group to see the opportunity here. It's a fierce competition, a fierce race, and the project here in Maine is really the United States flagship project for floating wind. So if you look here, these are a number of projects around the world that are going on, and these are our competitors. So this is in France, 3 projects are planned, 3 demonstration projects, each in the 24 megawatt range. So this is just what France is doing. Off Portugal, there's approved the 25 megawatt project. In 2017, there's a Scotland project that was just installed. In 2017, Japan has already put 3 turbines off. They're going to put 2 more. And Germany is planning about $1 billion right now of annual funding for offshore wind R&D, and a big focus on Florida. Going back to the U.S., where are we in terms of offshore wind? Well, right now there's only 1 farm, commercial scale. It's the Block Island Wind Farm, just put online here last year off Rhode Island. But there's a number of very big projects that are in the works. Particularly Massachusetts has 4 major lease areas that have been partially, some of them have been auctioned off. And then New York has a major New York lease sale. They're planning on 2.4 gigawatts by 2030. And a number of other projects down the Atlantic coast. So it's coming. There's a lot of momentum right now, we believe. And that Block Island project really hopefully is jump-starting everything here. But a lot going on right now. With that, I'd really like to open up just the floor to any questions. I believe Holly will be moderating that. I hope I gave everyone a nice overview of the technology history, how we got where we are, what are the challenges we're facing and where we're heading, and what the opportunity could be for the whole country here to start harnessing this huge offshore wind resource within about 50 miles of our coast. So I'll stop there and turn it back to Holly. Thank you very much for your attention.
Thank you, Anthony. So very interesting and admirable, all the work you've been doing, and exciting. I have a bunch of questions from people. And the first being, and Anthony, you can leave your share screen up perhaps with your contact information in case people should want to get in touch with you. But the first question I have is, how reliable is the wind off the coast of Maine? And can these offshore turbines produce power continuously uninterrupted?
Yep, that's a great question. The offshore wind is, in general, more reliable than onshore wind. And the reason that is very simple. You know, over the water, essentially a very unobstructed, clear path for the wind to follow. So the wind generally is much more uniform, much less variable, and also has higher wind speeds. So in general, you have a much more reliable wind resource. You also typically have a greater wind resource. We typically measure performance of wind turbines by a capacity factor, which is essentially a percentage of how, if you ran the turbine all year round at its rated power, so full power, how much of that will you produce at your site? So typically for on land turbines, you're looking in the 30% range. So you're producing about 30% of what you would produce if the turbine ran full speed all year. Offshore, you're looking at capacity factors around 40 to 50%. So there's a much bigger, a better bang for your buck, essentially, for an offshore project in terms of the wind and the amount of power you can produce. Of course, yeah. Of course, you have other costs you have to deal with. You have a floating foundation, you have a cable back to shore. So, but that's hopefully answers your question.
So so that could be continuously run uninterrupted?
Yeah, the turbines run basically if there's wind, they run, and if there isn't wind, they park. They also, if the winds get too high, typically over 50 miles an hour, they'll shut out. So what we do is we have wind speed data that basically you look at the probability of when you get winds, how often it's windy, and these turbines would be running, essentially you could think of it like 40 to 50% of the time. Yep.
Okay, thank you.
Yep.
And do you do any saltwater testing to understand how the corrosion will affect the system?
Yes, we do. In our laboratory, we have a saltwater accelerated corrosion type equipment to study those things in depth. Also, this unit was deployed offshore in saltwater, and so we were able to look at the corrosion as well. And then, of course, there are industry guidelines in terms of how you design concrete and steel that are based on the offshore oil and gas industry, which they've had structures out there for about 50 years, and then the bridge industry, which has saltwater piers and structures over the water. Yep.
Okay, thank you. I would think you'd be so thorough as to look at that. Can you comment, please, on how your tethering differs from the Highwind Scottish project that started delivering power in October?
Sure. Really, we're looking at a very similar, at least my understanding of their mooring system. They're using a large chain system, so essentially 3 chain anchors, chain moorings that tether the unit, go down to an anchor. So in terms of the actual mooring itself, it's a very similar system, which is a very conventional technology. The anchoring is a bit different. My understanding of their project, they have suction buckets, which are essentially large steel caissons, large diameter, and then they're essentially driven into the seabed, and that's their anchor. Whereas we're looking at using something more like a boat plow anchor, similar to what you might have on a boat, where you drop it and then pull it and then seat it. As you pull it, it actually seats into the mud. So that's what we're using in our project. But very similar systems. Yep.
So I understand you have all this fabulous equipment, to the wave machines there, but what about a storm that comes through and just totally tears things around in circles and creates havoc in a way that one can't really predict in a laboratory? How do you deal with these kind of crazy natural effects?
Sure. To deal with that, what we've done is we have that buoy we showed that's been out there for about 18 years.
Mm-hmm.
So we know we have a lot of data, at least in the last 18 years, that shows you what wind direction has occurred, with what wind speed, and at the same time what were the waves, and at the same time what were the currents, and so forth. So we had this database essentially. So then you start looking at statistics of these, and you estimate what's the extreme wind direction misalignment, say, with wave, and you start looking at those types of situations, and that's part of your engineering you have to do. And so all you can do really is look at the data you have. Of course, you have 18 years worth of data, and then you start building your environments based on that data. And luckily, we're not started from scratch in terms of how do you model wind and wave. We're building off the wind industry's experience, which is 30, 40 years of real data and measurements and modeling that they've developed to accurately simulate those types of events. And then also in the offshore oil and gas. So essentially, you take that data and then you use these types of tools that have been used for decades now, and then you simulate these types of environments. And then the goal of the equipment in the lab is essentially to check the key ones and make sure that your simulations, your numerical models are doing an adequate job.
It's great to see all the tests that were done and monitoring that's done on the natural world there. Wondering what kind of pushback you're getting from local people?
Sure. Yeah. Yeah, well, there's been a very big, a major part of this project, which I didn't spend too much time on, is the outreach portion. We have a very strong team of folks that are working with the communities that can be affected by this project. So for example, on Monhegan Island, they're the closest folks, the folks that will be able to see this. There's been, from the very beginning, essentially a community benefits, we're required by law to have a community benefits agreement with them, where they are the community benefits through at one time they talked about having a cable to shore where they got essentially free energy or an equivalent cost benefit. So this is the kinds of negotiations that are taking place to make sure that, look, we understand putting 2 turbines in their backyard is going to be an impact, and how do we make that right in the best way we can. So there's been a huge effort from our team here to make that happen, in hundreds of meetings, literally, with those folks on the island to come up with an agreement that hopefully works for everyone. Yeah. So there's the huge, I can't tell you how much effort is going on to try and, again, minimize impacts to everyone that will be affected by this project. Yeah.
Okay. So in that regard, how close can boaters and fishermen get to these turbines?
So we haven't settled on a final number, but looking at the Highwind Scotland project that you brought up, they're allowing their boaters to go within about 150 feet or so of the units. And so we expect to have something similar for our project.
Okay, thank
so not
you.
A huge, yeah.
What opportunities are there for Maine businesses to participate?
Sure. So we're already engaging with a number of Maine businesses. You saw it on some of the other slides. We're working with Chimbro, which is a large civil construction firm. But we envision a lot of opportunities to work with folks in the construction, just the support of that construction. We'll have to mobilize quite a labor force, quite a group of different vendors to support supplying different materials. We also envision working with the locals on the island to help support different O&M and different activities for the units. So we expect that there'll be some. We've already been working with a number of them to do some of the initial testing offshore with the buoy. We've been also working on the island in the outreach and the environmental monitoring aspects. So there'll be a number of ways for folks to get involved. And ultimately, where we see the technology, if this is all successful and we demonstrate these units, we really envision that we could build these hulls here in Maine and then export them down the East Coast. So we could essentially have, in many ways, another Bath Iron Works, but this is a concrete floating wind turbine yard where we build the hulls, we launch them and float them down the East Coast and start to supply the large markets that are developing off Massachusetts and New York and other states. So that's really the long-term vision and that we want to get. We want to really hopefully create an industry here and bring jobs back to Maine. And that's really my mission here is in developing this technology is hopefully to help that piece of the Maine puzzle.
And is the state of Maine supporting you in this effort?
Yeah, we've had a very strong support through the legislature and also our congressional delegation. It's been, again, we've been at this for over 10 years and through multiple administrations and multiple cycles of the government. I like to think I'm not personally involved in those day-to-day movements and negotiations and discussions, but I feel like we've had strong support all along.
Well, that's good to hear. And what role have students played in this project? Are they involved at all?
Yeah, absolutely. This is one of the parts that goes to our core mission at our center, which is to educate students and put them first. So the students on this project have really made huge contributions. We've had about 6 master's and PhD students get minted from this. We've had probably over 30 maybe 40 undergraduate students who've been trained in a whole variety of aspects, everything from engineering to ocean engineering to construction to testing to outreach to involvement in the environmental studies. So really, I mean, this investment that's been coming from the U.S. Department of Energy has also trained a lot of Mainers at the same time, and that's including myself. I'm from Maine, originally grew up in the Washington County area, and I've been trained on this project, got my PhD, and now we're charging ahead here. So there's been a huge, in terms of investment in our people, I can speak as a prime example of that. That there's been a huge increase in terms of our workforce in this area. And it's very unique in the world.
Oh, I'm sorry. I didn't realize I was muted. I wanted to thank you, but I have one more question that came in saying, when would you expect to begin delivering power to the grid?
We're targeting right now to get these online sometime between 2020, roughly 2020 is when we think the construction will be complete. But there's a lot of steps to get from here to there. So, but 2020 is the current estimate.
Okay. Well, it's been very impressive what you've been doing, and we thank you for all your time and effort. We will have this recorded up on our website for those who may have missed it, and I wanted to invite everybody to our next brown bag webinar, which will be again on a Thursday, February 8th, again at the same time at 1 o'clock, where we will have Anne-Marie Boulet come and talk, and and she will be talking about Discover Aware, the global consensus of water scarcity for LCA. So again, thank you, Dr. Viselli. We wish you all the best in your work ahead and more great energy. So thank you, and I'll close this webinar, and have a great day, everybody.
Thank you all for your attention. Please feel free to call me if you have any questions or would like to discuss more.
Okay, thank you.